Hi students, welcome back. Today we are going to see the remaining question of the Abhyas mock test question paper number 2. Okay, so let's get started. See, question number 81. Bakelite and polythene are considered as an example of. Okay, so they have given a set of options. You have to choose whether it is a thermosetting plastic or thermoplastic. Okay, so what is thermosetting plastic, students? So which are permanently get molded on heating followed by cooling. Okay, so if they take a shape, okay, so it is permanent, and after that it becomes very rigid. Even if you supply very heat, it is resistant to that. So examples are bakelite, epoxy resins, and vulcanizing rubber. And thermoplastics is contrary to that, so can be remolded number of times. So examples are polystyrene, nylon, and acrylic. So your bakelite is an example of thermosetting, and polythene is an example of thermoplastic polymer. So it is option 4. So next question. Photochemical smog consists of excessive amount of X in addition to aldehydes, ketones, and peroxyacetyl. Okay, so which is the abbreviation is PAN. What is X? See here the set of options are given, which is methane, carbon dioxide, and this must be ozone, students, not oxygen. Ozone and carbon monoxide. See, what are photochemical smogs? See, photochemical smogs are created by the volatile organic compounds. It is a kind of pollutant created in the atmosphere, okay, and your nitrogen dioxide and ozone. So what happens here? So when your nitrogen oxide, okay, in presence of sunlight, what happens? It get dissociated into nitric oxide and your radical oxygen, so which is a gas. So this oxygen, what happens? It reacts with the oxygen in the air. Okay, it reacts with the oxygen in the air to create ozone. So this is an excellent oxidizing reagent as well as toxic also. See, this ozone, what it does, this ozone in turn reacts with the nitric oxide. So it is a oxidizing agent, no? So it recreates, okay, it is your nitrogen dioxide gets regenerated. Okay, students, so this ozone, okay, what in turn it will your volatile organic compounds such as methane in the atmosphere, it reacts to form formaldehyde, to form ketones, and number of like peroxyacetyl, number of other pollutants. So other than aldehydes, ketones, and PAN, the X is ozone. Okay, so which of the following statements is incorrect? So before, resonance is what, students? Resonance is the delocalization of electrons. So here we have to find out which statement is incorrect. So before that, I will give you a brief introduction about the resonance. See, students, it is a delocalization of electrons. For example, if we take in this molecule, okay, these electrons will involve in resonance, giving rise to two resonance structures. Okay, so it need not be the two resonance structures, it need not be same in stability or same in energy. You know that stability and energy are inversely proportional. More the stability, the less will be the energy. So if you have more the two resonance structures, it need not be necessary that it must have the same energy or same stability. Here this is more stable, so this is more stable and less in energy, okay, being the major contributor to the resonance hybrid. So the resonance hybrid has been derived from the number of resonance structures that is possible. Okay, so this is the resonance hybrid. So the major contributing resonance structure will be the most stable and which has the less energy. So here when you take, this is most stable and this is the major contributor to this resonance hybrid. Okay, so and here these two resonance structures are equivalent. You see, they are very symmetrical, they are very equivalent, they contribute in equal proportion. These contribute equal. Okay, so the resonance structures which are equivalent in structures give the higher resonance energy. So the resonance energy means what? More stability. Resonance energy means lower in energy and more stability. Okay, so So based on this we can check whether which option is incorrect. Different resonating structures contribute to the resonance hybrid in proportion of their energies. See, first it's this option is wrong because the different resonating structures contribute to the resonance hybrid inversely proportional to their energy. Okay, their contribution will be inversely proportional to their energy, not directly proportional. It is directly proportional to their stability. More the stability, more the contribution. Okay, so this statement is wrong. Equivalent resonating structures result in higher resonance energy. Yes, equal resonating structures contribute more to the resonance energy. Higher resonance energy means you should not mistake that high resonance energy. Higher resonance energy means higher stability. Here resonance energy, no, you must think in the way of stability. Okay, so the resonating structures represent hypothetical molecules having no real existence. That is true. The resonating structures are less stable than the resonance hybrid, because the resonance hybrid which has been derived from the resonance structures is the most stable. Okay, so the resonance structures are less stable than the corresponding resonance hybrid. So next questions. In some solutions, the concentration of H3O plus ions, okay, remains constant even when small amounts of strong acids and strong bases are added to them. These solutions, you know, ideal solutions, colloidal solutions, true solutions, it is buffer solutions. And you know, in acidic buffer solutions, the pH is equal to pKa plus log concentration of salt divided by the concentration of the acid. So what is a buffer solution, students? For acidic buffer solutions, it is a solution of a weak acid and its corresponding salt with the stronger base. Okay, if you add, and this is the buffer solutions, if you add any amount of H plus immediately, okay, what reaction will take place? See, CH3Na, this salt, no, it reacts with H plus, immediately it will give you the corresponding acid. Okay, so thereby whatever H plus you have added, it will get consumed. If you add OH minus ions, the corresponding acid will react, giving rise to, okay, the corresponding weak, the strong. This way, if you add small amount of strong acid or base, it will not affect the pH. Okay, so the answer is buffer solutions here. Among the following, the narrow spectrum antibiotic is penicillin G, so ampicillin, amoxicillin, and chloramphenicol. The answer is penicillin G. Okay, so which reaction is suitable for preparing alpha chloroacetic acid? So what is alpha chloroacetic acid, students? So CH2, this is Cl, this is COH. Okay, so this is alpha chloroacetic acid. And how it can be prepared? It can be prepared from the corresponding acetic acid using red phosphorus, and we are going to do chlorination, so we have to use the chlorine. So first reaction, what happens? Okay, this OH will get, okay, converted to this one, and the red phosphorus once again it will react. This is an alpha acidic hydrogen, isn't it? So this is an alpha hydrogen which is adjacent to the electron withdrawing carbonyl group. This is an alpha hydrogen which is very acidic in nature. So this, the chlorination takes place here. Okay, then you have to do hydrolysis. After hydrolysis, you will get the corresponding acetic acid. This chlorine will be replaced by OH once again, and this chlorine remains untouched. Okay, so the answer is Hell-Ohlhard-Zielinski reaction. It is a naming reaction. Okay, students. So here, next question. A mixture of methane and ethane in a molar ratio of X is to Y has an average molecular mass of 20. The mean molar mass when they are mixed in the molar ratio of Y is to X will be. So this is the given data, students. So we have mixed the two gases. Okay, so methane and ethane. Okay, so we know the molecular weight of methane is 16 grams and ethane is 28 grams. So according to this formula, and what they did, they mixed X moles of methane and X moles of ethane, and they found that the mean molar mass to be 20. Okay, so they are asking if they are mixed in the ratio. y is to x, what will be the mean molar mass? Okay, they are asking this. Okay, if they are mixed in this ratio. So first of all, what is the formula for mean molar mass? See, it is the molecular, we have mixed the methane and ethane here, so it is the molecular weight of methane into the number of moles. Okay, so this is also x, okay, into x plus this is molecular weight of ethane into, so the number of moles mixed is y, okay, divided by total number of moles, and they have given the value to be 20. Okay, if we solve this equation, this is 16x plus 28y equal to 20x plus 20y. If you solve this, so 20x is equal to 8y, so x is equal to 2y. This relation we got. Okay, so if methane and ethane were mixed in this molar ratio, okay, so what will be the formula? So this is 16 into y plus 28 into x divided by x plus y. So we know the value of x, isn't it? So we can substitute the value of x here. So 16y plus 28 into 2y divided by x plus y is what? 2y plus y. Okay, so 16y plus 56y divided by 3y. Okay, so it is 72y divided by 3y, which is equal to 24. So the mean molar mass is 24 here. So the option is 3. So for a given reaction, energy of activation of forward reaction is 80 kilojoules per mole, and the enthalpy is minus 40 kilojoules per mole. A catalyst lowers the activation energy of the forward reaction to 20 kilojoules per mole. What is the ratio of energy of activation for reverse reaction before and after addition of catalyst? See students, what they have said, they have did a reaction. Okay, so this is your reactant. Okay, they started the reaction. So for getting the product, this is it has to cross the activation energy, and then only we will get the product. Okay, and this is an exothermic reaction. Where I got the data? Because del H is minus 40 kilojoules per mole. Here energy is liberated, so the energy of the product must be lesser than the reactant. So this is what we got. This is an exothermic reaction. Okay, so this is an exothermic reaction. So what data we got from here? See, for this reaction to occur, it has to cross an activation energy, which is the total length, the total energy length is kilojoules per mole, and this is the activation energy of the forward reaction. And we also got a thing that this is 40. This is 40. How I got? Because this much energy is released. Okay, so the product is 40 kilojoules per mole lesser than the reactant. Minus, see, del H is equal to minus 40 kilojoules per mole. That means minus, negative means liberated. Okay, so nothing to do with the sign. It says that the energy has been liberated. It's an exothermic reaction. So the product is 40 kilojoules per mole lesser than the product. So this is the height. So they are asking, okay, so this is for the forward reaction. For the backward reaction, what is the energy of activation? And if so, another scenario is that they add a catalyst. What they are doing? They are adding a catalyst. Okay, so when adding a catalyst, the energy of activation, okay, this length, okay, so minimizes, okay, so minimizes to kilojoules per mole. So that is the action of the catalyst. If you add catalyst, the energy of activation decreases, so the reaction happens very fast. Okay, so they are asking that what is the energy of activation for the backward reaction, okay, with catalyst, and without catalyst. Okay, so we are going to do this. See, what is the energy of activation here? Energy of activation of the forward reaction. For the forward reaction to happen, we have to supply 80 kilojoules per mole, and this happens without catalyst. and the energy of activation for the backward reaction same without catalyst we have to find out. So what is that? This is the backward reaction, students. This is the backward reaction. Check the black mark, that is a without catalyst. Okay, so what energy you have to supply from the product to reactant? This 40, this much energy you have to supply. This much energy. What is that energy? From here to this point, from this point to this point is 40, from this point to this point is 80. So 80 plus 40 kilojoules per mole, which is 120 kilojoules per mole. That is the energy of activation for the backward reaction without catalyst. Okay, so what happens to the energy of activation of the forward reaction with catalyst? Okay, with catalyst. See, with catalyst you have to supply only 20 kilojoules per mole. Okay, so this is what? Kilojoules per mole. So what happens to the backward reaction? See, what energy you have to supply for the backward reaction with catalyst? So you have to supply an energy of this much energy. So from this point to this point is 40, we already know. From this point to this point is 20, because the catalyst, so adding catalyst, okay, will favor both forward and backward reactions. Okay, so here you have to supply 40 plus 20, which is 60 kilojoules per mole, and they are asking the ratio of this one with catalyst and without catalyst. So energy of activation backward reaction without catalyst is 120, and energy of activation, okay, so this is without catalyst and this is catalyst, so 60, which is 2. So the ratio is what? So the ratio is 2. So the next question, 3 Faradays of electricity was passed through an aqueous solution of iron 2 bromide. The weight of iron metal deposited at the cathode. Okay, so here please listen here, students. So first of all, we need to write the reaction. Say here iron 2 bromide is what? So only iron 2 plus is there. So if you write that, that is sufficient. So this is what? Iron 2 plus. So you need 2 moles of electrons to get iron. Okay, so this 2 moles of electrons is, when speaking in terms of moles, this is 2 moles of electrons. When you speak in terms of charge, see what is charge? The charge of 1 mole of electrons. 1 mole of electrons, we call it as 1 Faraday, which is 96,500 coulombs. Okay, so how much charge we are passing? For this reaction to happen in terms of charge, we have to pass 2 Faraday. Okay, and they have asked in terms of grams, and you know that this is what? 2 Faraday. While passing 2 Faraday of charge, you are getting 1 mole of iron. So in terms of grams, it is 56 grams. Okay, and they are asking what will happen if they pass 3 Faradays of current. Okay, while passing 2 Faraday of current, Faraday of charge or current, you will get 56 grams of iron. You are going to pass 3F, that is 3 Faraday. Okay, so 3 into 56 divided by 2, which is 84. Okay, so the answer is 84 grams. Then the cyclohexene on ozonolysis followed by reaction with zinc dust and water gives compound E, and compound E on further treatment with aqueous KOH results yields compound F. What is the compound F? So okay, so what is cyclohexene, students? So this is your cyclohexene, and you know the ozonolysis first step and followed by using zinc dust. Okay, you will get what is the reaction on the double bond, students? So here in the double bond will get cleaved, and this carbon will get a carbonyl, and this carbon will get a carbonyl. This double bond will get cleaved. So you have to write the rest of the things. No carbon lossage. Okay, so there is no carbon lossage. See, there is 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon. Those will be retained. Only the connectivity between these 2 carbon will be broke. Okay, so I'm rewriting as it is. Okay, so you will get a carbonyl here, and one hydrogen was already there, and that is that. Okay, so you will get a dialdehyde first. So here then we are going to treat with aqueous KOH. So the treatment with aqueous KOH, immediately you think of condensation reaction, that is Aldol condensation. See, there are, you see, this is also acidic hydrogen, this is also acidic hydrogen. Okay, so and we have carbonyl. What is ingredients for the aldehyde? You need alpha hydrogen, alpha acidic hydrogen, and a carbonyl. That's all. No. So what happens? Here the KOH is a base, so it will know, it is perfectly symmetrical, so it will go and abstract this proton. So in turn what you will get, the rest of the things will be written. This is CHO, here a carbonyl, this anion will go and attack this carbonyl. Okay, so the aldol condensation is going to take place. So first step you will get a OH. Okay, here a 5-membered ring, 1 2 3 4 5 membered ring. So to this carbon, this aldehyde group is attached. I am writing this. Okay, you see there is one more hydrogen here, again that will get, okay, while treating with KOH, that is a base. Okay, that hydrogen will also get deprotonated. So here you will get a 5-membered ring, okay, with CHO. Okay, so it is symmetric. Okay, don't get confused if I tilt this. Okay, so the option is okay. Okay, students, thanks for watching.